Doppler shift. Doppler shift correspond to the change in the observed frequency of a wave if the source of the wave and the observer are moving with a relative velocity with respect to each other. Here we consider Doppler shift in electromagnetic waves. The electric field vector in an electromagnetic wave is represented by the equation, the vector E as a function of r and t, where r represents the position vector and t the time coordinate is equal to a vector, constant vector E0, which correspond to the amplitude of the electric field, its direction representing the polarization, times e to the power I k dot r minus omega t, where k is called the wave vector of the electromagnetic wave and omega its angular frequency. Now the wave vector k can be written as its magnitude times a unit vector, and the magnitude of the wave vector which is represented by k is related to the wavelength of the electromagnetic wave as k equal to 2 pi by lambda, where lambda is the wavelength of the EM wave. Now, if c is the speed of the electromagnetic wave, we know that it is related to the frequency and the wavelength via the formula c equal to nu times lambda, where nu is the frequency of the wave. So this would mean that lambda equal to c by nu, and therefore k will become 2 pi by c times nu. Further, in an electromagnetic wave, the frequency, the angular frequency omega and k are related by the formula omega equal to ck. Now since k equal to 2 pi nu by c, this means omega equal to 2 pi nu. Now the electromagnetic field vector can be written in the following way: E equal to E0 times exponential I phi of RT, where phi of RT is the phase factor of this wave, and which we have found to be equal to k dot r minus omega t. Now k equal to 2 pi nu by c times unit vector k, then r is r, minus omega equal to 2 pi nu times t. So together we can write this as, taking 2 pi nu outside, as 2 pi nu times k cap dot r by c minus t. Now the frame in which the position and time are measured here in this expression will be called the frame S. And then we consider another inertial frame that is moving with a constant relative velocity v along the x-axis with respect to the frame S. And in the frame S dash, the coordinates are given by x dash, y dash, z dash and t dash. So for any event which is represented by coordinates x, y, z and t, the corresponding coordinates in the frame S dash, denoted by x dash, y dash, z dash and t dash, are given by the corresponding Lorentz transformations, which are given by equations 1.3, which says that x dash is equal to gamma times x minus vt, where v is the speed with respect with which the frame S dash is moving relative to S along the x-axis, and the factor gamma is 1 by square root of 1 minus v square by c square. Now y dash and z dash doesn't change, and t dash becomes gamma times t minus v by c square times x. Now, the phase of this electromagnetic wave at a particular event, say represented by x, y, z and t in frame S, and x dash, y dash, z dash and t dash in frame S dash, should be the same. So that means phi at x dash, y dash, z dash, t dash is equal to phi at x, y, z, t. Now phi is given by the formula nu times k dot r by c minus t. Now denoting the frequency of the electromagnetic wave in the frame S dash by nu dash, its wave vector by k dash, and position vector by r dash and time by t dash, we have this relation written in the following way: nu dash times k cap dash dot r dash by c minus t dash equal to nu times k dot r by c minus t. Now we assume that the wave, electromagnetic wave, is propagating in along, say, a direction k, which is making an angle theta with the x-axis in the frame S. And we assume that this vector k is lying in the xy plane. Since the frame S dash is only moving along the x-axis with some velocity, say v, we can also see that in the frame S dash as well, the wave vector k dash of the electromagnetic wave lie in the xy plane. So in the S dash frame, we assume that the wave vector k cap, the unit vector k dash cap in the direction of the wave vector makes an angle theta dash with the x-axis. So in the frame S, the wave vector makes an angle theta with the x-axis, and in the frame S dash, the wave vector k dash makes an angle theta dash with the x-axis. And since we have assumed that the k vector lies in the xy plane in the S prime, it will lie in the x dash y dash plane in the S dash frame as well. So now the unit vector k dash can be resolved into its components. It makes an angle theta with the x-axis, and therefore its component along the x-axis is its magnitude times cosine of theta. K is a unit vector, and therefore its magnitude is 1, and therefore the x component is given by cos theta. And similarly, the y component is its magnitude times sine theta. Magnitude is 1 and is sine theta. And since we have assumed that k lies in the xy plane completely, the y component is 0. And similarly, the wave vector, the direction of the wave vector k dash in the S dash prime is written in terms of its components in the following way. It makes an angle theta dash with the x dash axis, and therefore the x dash component would be its magnitude times cosine of theta dash. Again, the magnitude is 1, so we get cosine theta dash, sine theta dash, and since this k dash is also in the x dash y dash plane, the z dash component is 0. So we have these two expressions for k and k dash. And we can substitute this in equation 1.4, and then k cap dash dot r dash can be written as k cap x dash plus k dash y dash plus k dash z z dash. But then k dash x is cosine theta dash, x dash is x dash. So the first term is x dash cosine theta dash, and that is what we have over here. And the second term is k dash y, which is sine theta dash times y dash, and that is what this is. And the third term is k dash z, which is 0 times z dash, and that is 0. So the factor k cap dash dot r dash become x dash cos theta dash plus y dash sin theta dash. Now the factor of c in the denominator is written as c itself and t dash as t dash. And on the right hand side, equivalently, using this expression for k, we can write it as x cos theta plus y sin theta by c minus t. Now this x dash, y dash and t dash are related to x, y and t via the Lorentz transformations given by equation 1.3. So here in this equation, we substitute for x dash, y dash and t dash using this equation. So that on the left side and on the right hand side, we have only expressions involving x, y and t. If we do that, we will get the following equation. Nu dash, then x dash is given by gamma times x minus vt cos theta dash. Now y dash is equal to y, and therefore I can simply write y here, sin theta dash by c minus gamma t dash, right? So this is so this is t dash. T dash is gamma of t minus v by c square x, and that is equal to the right hand side, which is this one. So nu times x cos theta plus y sin theta by c minus t, and this should be true for any event in the space time, and therefore the coefficient of x on the right hand side of this equation should be equal to the coefficient of x on the right hand side, and similarly the coefficient of each of these variables and their powers should be the same on either side of this equation. We now equate the coefficients of t on either side. So let us find out the coefficient of t on the left hand side. So we have a nu dash here, a gamma here, minus v here. So minus gamma nu dash v times t, then cos theta dash. So cos theta dash. Okay. And the other factor is this one, minus gamma times nu dash. Minus gamma times nu dash. Oh, sorry, this has a factor of c in the denominator as well. So on the left hand side, the coefficient of t dash is minus gamma nu dash, then b cos theta dash by c plus 1. And on the right hand side, the coefficient is coming from this term, so that is simply minus nu. So this should be equal to minus nu. Or in other words, removing this minus sign, nu should be equal to gamma nu dash times 1 plus b by c times cosine of theta dash. So that is this equation. So we see that the frequency of the electromagnetic wave in the two frames that are moving with a finite relative velocity are different, given by nu and nu dash, and are related by this expression. Now we consider a special case of this called the longitudinal Doppler effect. For this, we consider an observer moving away from the source of the light with the velocity v along the x-axis. So we have S dash, which is the frame that is fixed to an observer moving with a velocity v along the x-axis with respect to S, which is fixed on the source. Now, this observer observes a light beam coming from the source. The light beam that is coming towards him. So, for him, the light beam is coming in this direction, so that it will be along the x dash axis. X dash axis is the x axis corresponding to the S dash frame, the frame that is attached to him. Since the light wave is coming towards him and it is along the x axis, the angle it makes with the x dash axis is 0. So that means theta dash is equal to 0. Now substituting this in this expression, we have nu equal to gamma nu dash times 1 plus v by c. Cosine of theta dash now is 0. Cosine of 0 is 1, and therefore we will get this expression. Now the factor of gamma is square root of 1 minus v square by c square. Now this factor 1 plus v by c can be written as square root of 1 plus v by c square, and this the denominator factor 1 minus v square by c square can be written as 1 minus v by c times 1 plus v by c. Now a 1 plus v by c factor from this is cancelled by 1 plus v by c in the denominator, and the result would be square root of 1 plus v by c divided by square root of 1 minus v by c. So this is equal to 1 by square root of c times c plus v divided by, again in the denominator, this is 1 by square root of c times c minus v. And cancelling this term, we will get this equal to square root of c plus v by c minus v. So that is this equation. So the observer is moving along the x-axis with respect to the source with a velocity v. Then the frequency nu, which is the frequency in the frame S, or in other words, it is the frequency when the light is emitted by the source in its frame of reference, in the frame of reference in which the source is at rest. That is given by nu, and nu dash is the frequency measured by the observer in the frame S dash. And nu dash are related by this equation. Assuming that the light is coming towards him, the observer, from the source, so that it is along the x-axis, and therefore theta dash is equal to 0. So nu equal to nu dash times square root of c plus v by c minus v. Or in other words, nu dash is equal to nu times square root of c minus v by c plus v. So now the numerator has a factor of c minus v and the denominator has a factor of c plus v. Now the observer is moving away from the source. So v is in fact a positive number. So c minus v is less than c plus v, and therefore nu dash is less than nu, because square root of c minus v by c plus v is less than 1. The numerator is smaller than the denominator. So we immediately see that if the observer is moving away from the source, then the observed frequency nu dash will be smaller than the original frequency nu with respect to with which the light has been emitted by the source. Or in other words, if the source and the observer are moving away from each other, the observed frequency will be smaller than the emitted frequency. Now we consider the example of the observer moving towards the source. This is similar to this situation, except the fact that S dash is actually now moving in this direction with velocity v. So this is obtained, the corresponding expression is obtained by changing v to minus v in this expression. So we will have, in this case, nu dash is equal to square root of, nu times square root of c plus v by c minus v, which is obtained from this equation by changing v to minus v. Because now the observer is moving in the opposite direction to the case we considered here. So in that case, since c plus v is greater than c minus v, the observed frequency nu dash will be greater than the emitted frequency nu. So the observed frequency nu dash is larger than the frequency nu, the emitted frequency nu, when the observer is moving towards the source, or in other words, the source and observer are moving towards each other.